Okay, here's three problems from section 5.7 we're going to look at. 411 looks really daunting, but if you pick the correct value for u, it falls right out kind of nicely. Notice if you pick u equals the inverse sine, the derivative of that is 1 over the square root of 1 minus t squared dt. Notice now when we substitute in, that's exactly what we have. This is just going to go to the du. This is just going to go to u, and we don't have to worry about any constants or anything. So this just becomes the integral of u to u. When we integrate that, then we get u squared over 2 plus c, and we plug in that u is equal to the inverse sine function. So this would be our answer for 411. Again, notice the trick is just picking the right value for u. 414 is actually similar. It's a little bit trickier. But notice here, let's pick the u equals the inverse tangent of t squared. Now in this case, when I take derivative of u, I do have to use the chain rule. So the derivative of the inverse tangent function is 1 over 1 plus something squared. But remember, we have to keep the inside square alone. So this says t squared, 1 over whatever. So that's the derivative of the outside. Leave the inside function alone, times the derivative of the inside function, which is 2t dt, like that. Now let's simplify that a little bit. Let's write this as 2t over 1 plus t to the fourth dt. And the way I have it written, actually, this is a problem. Notice I've got a t here, and I don't have a t there, but in looking back at the problem, thankfully, I see that I miscopied the problem. That t has to be there, otherwise we got big problems. I can fix the 2. So notice I can put a 2 here and divide by 2. That's not a problem. But I have to have that 2t, I have to have everything to be accounted for. So now I have 2t dt, 1 over t to the fourth. Notice that all turns into du. And it looks like we get 1/2. And then we get, this just goes to u, du. Everything's accounted for. This goes to u, everything else goes to du. So now we can integrate. This is u squared over 2 plus c. Put in what we had for u, so we get u, whoops, I don't want that. I want u squared, which is the inverse tangent of t squared, that quantity squared, all over 4. 4 from 2 times 2 plus c. And some of these answers are quite intimidating perhaps, but that's what they are. So that's what it is. So that should be the answer to 414. Again, thankfully I miscopied that problem, otherwise I would have been stuck. 426. Guess what? It's another u substitution problem. In this case, I'm going to pick u equals ln of t. So this is going to become my u. Note, remember the derivative of ln of t is 1 over t dt. And thankfully, we have a 1 over t dt. That's just going to become my du. And it looks like when I do my substitution then, I'm going to get 1 plus u squared. Notice the natural logarithm squared, so this becomes u squared. Now, looking at our integration formulas for this section, this looks a lot like the arctangent one. It looks like this will just be the arctangent function. Remember, the antiderivative of this is 1 over a times the arctangent, or the inverse tangent of u over a plus c. In this case, this has to be a squared, so it looks like a has to be 1, and we already have the terms in there u. So this is just 1 over 1, or 1, times the inverse tangent of u, which by the way is the ln of t. A is just 1, so these guys just become 1. And that should be what we want for the answer to that one. Let me double check here, see if that looks like what I had previously for the answer. Yeah, it's the inverse tangent of the ln of t plus a constant. And we got all three of them.